So, welcome to the 19th edition of our GO2NE Global Ocean Oxygen Network webinar. I'm Andreas Oschlies, our system model at GEOMAR Kiel and co-chair of GO2NE. And I'm very happy to have two excellent speakers today here. I will introduce shortly. Before we start, a few housekeeping rules. So the audience, that's all of you, you cannot directly speak to us. You have to use the Q&A box to put in your questions there. And then after each of the talks, these are 20 minutes each, we have a 10-minute discussion slot where I will then moderate the discussion and read your questions from your Q&A box. So I depend on you, on your questions, and you have to type it in. That's our way of communication here today. Please do not use the chat, use the Q&A box, please. And a quick announcement. So you can sign up, you should sign up to the Global Ocean Oxygen Network and the Global Ocean Oxygen Decade Good newsletter. You can scan the symbol here, and then you'll receive the good news about oxygen deoxygenation every few months. And the next edition is coming up soon around Easter. So that's the announcements. And now we go to our first speaker. That's Javier Arístegui. He's a biological oceanographer at Las Palmas, Gran Canaria Islands. And he's also the director of the UNESCO Chair on Environmental and Marine Resource Management. And he co-chairs the SCORE group WIMO on mesopelagic respiration in the ocean. And that's also what he will talk about us today with the perspective on oxygen. Javier, the floor is yours.
Thank you. Okay.
Yes, perfect.
Can you see my screen?
Yes, perfect.
Okay, perfect. So the talk is about estimating dark ocean respiration through the enzymatic ETS activity. And this is a task that we are running in several projects of the European Union and this SCORE working group, and also national projects. We can assess the biological pump, which is the transfer of carbon from the surface ocean to the deep ocean, by two main ways. One is looking at the carbon fluxes. The other way is the other side of the coin, which is trying to look at the respiration of this carbon that is transported in the water column, and this should be balanced in some way. It's not easy. I mean, in theory, it should be more straightforward to measure respiration because there are so many mechanisms involved in the transfer of carbon from pure dissolved carbon to large particles to the deep ocean that sometimes it's hard to combine and reconcile all these fluxes together and try to sum them up. Just looking, for instance, the suite of physical processes that they are transporting DOC and low sinking POC in the water, like overturning circulation, diffusion, isoprenal transport, subduction, and some others. This is a very, very complex suite of physical processes operating at different scales and in different regions. The same happens with the gravitational flux, which there is some interference with the active flux, which is channeled by crustaceans and fishes, because part of the excretions of this organism may come into the gravitational flux. So it's not an easy task, and that's the work of many, many scientists in the world that are trying to put numbers to these fluxes. So at the end, we need to have like this balance. Most of the respiration of this organic carbon is mediated by microbes. And that's what we are going to talk here, basically, how we can address this. There are basically two different approaches. One is the large one. The large approach is biochemical approaches, like looking at changes in oxygen fields, for instance, deriving oxygen utilization rates from apparent oxygen utilization and knowing the age of the water masses, or doing mass balance box model studies of carbon, DOC and POC, or looking at advection diffusion models from oxygen or other biology global circulation models. In general, this should be the gold standard because they integrate long-term and large-scale processes and avoid sampling cluster and manipulation. But anything is not crystal clear. So there are some cons. There are uncertainty in the fluxes, there are mixing effects, uncertainty in eddy diffusivity, and all these models need independent verification. Haichao is going to talk us about some of these processes, so I'm not going to get into detail here. The other large approaches is to look at the ecological approach. Here we can look at bulk in vitro oxygen consumption by incubating samples in bottles or respiration chambers and using optodes or microwinkler or mass spectrometry to look at this change in oxygen consumption. We can also look at the single cell respiration by redox dyes like CTC or the redox sensor green, which has been recently used. But also we can, if we know the prokaryotic growth efficiency, we can derive prokaryotic respiration. But this is like a vicious circle where we need to derive prokaryotic growth efficiency knowing prokaryotic respiration. And at the end, we have also enzymatic measurement like the ETS activity that I'm going to talk about in this presentation. So the pros of these methodologies, they are somewhat more precise and differentiate ecological processes, but there are many cons. We only address short-term, spatial and temporal variability. Many of these processes rely, or methodologies rely on conversion factors. And what about sample manipulation in the incubating bottles or chambers? And what about the pressure effects? So none of the methods are perfect, and we have to deal with them. So the ETS activity is a fast-sensitive method that one of the good things is allows collecting a large number of samples, increasing the resolution in depth, and also avoid bottle and pressure effects because we don't manipulate the samples. This method was introduced by Ted Parker in the 70s. It measures potential respiration by detecting the respiratory electron transfer activity in the dehydrogenases and cytochromes that control respiration. And collectively, all these enzymes are known as the respiratory electron transport system. So all these work at maximum level of activity, adding saturating levels of paradigm substrate like NADH or NADPH to stimulate the enzyme's activity. And at the end, we use INT as an electroacceptor in replacement of oxygen to reduce to INT formation, we produce the red color that we can measure in the spectrophotometer. Sorry. So what is the wrong thing here is that the chill potential rate, and we need to convert this to actual rates. And how the RETS ratio varies. Does it vary according to the metabolic state of the organism? Does it vary according to the quality of the substrates? Does it vary according to temperature in the different way? We know very, very little about this. We have some interesting information from the past years on the relationship between respiration and ETS in the surface ocean. There's a pretty good correlation between respiration and ETS, putting all the data together. But we are aware that there is variability, local variability, regional variability, and it depends mainly on what is the composition of the community, if it's dominated by phytoplankton or bacteria, and how is the productive the community. But in general, all put together, there is a pretty good correlation here. So what we need is to constrain the variability of this correlation in different regional areas here. And what we know from the deep ocean, almost nothing. as far as I know, there are like only 3 studies published, and they are all studies, in fact. One of the most interesting to me is this study with marine bacteria that were cultured in a batch mode by Christensen and co-workers. And they observed that during the growth phase of the bacteria, the RETS was close to 1, and during the senescent phase, the respiration dropped down, while ETS remained almost stable, and the RETS dropped down to near 0.1. So one would assume that depending on the activity of the bacteria and the substrates, the RETS would range between, let's say, 1 and 0.1. In a field study in the Canary current some years ago, we obtained RETS, which was close to 0.7, which is something that is consistent with a culture experiment by Christensen and co-workers. But later on another study in the North Atlantic, we got unrealistic values of near 5, which means that in this case, actual respiration is higher than potential respiration, which is something hardly explained, at least in considering what enzymatic activities are assumed to represent here. One difference between the Canary current and the North Atlantic study was that in the first study, we did a backscaling. What is a backscaling? So we look at during 3 days, how inside the bottles, bacteria grew up and changed in abundance, and there were changes also in prokaryotic activity. So what we do is we correlated the oxygen consumption with the growth in the prokaryotic abundance and the heterotrophic production, and use these regressions to backscale to the initial values. And that way respiration was reduced and was more realistic than it would have if we only took the end time of the experiment, of the incubation. More recently, in a Mediterranean cruise, which is, as you know, a very oligotrophic region, we measure in the meso and bathypelagic layers also respiration and ETS. The respiration was measured by means of mass spectrometry, as you can see in the upper left panel. And the RETS ratio of the 13 sample that we measure, the 13 experiment, carried out from 24 to 48 hours, they yield a value close to what Christensen and co-workers found as senescent bacteria, so close to 0.1. In fact, we use a similar value like this when 20 years ago, with the data that was published in the literature, was about 600 data, we estimated at a global scale what was the mesopelagic respiration, the average mesopelagic respiration in the oceans. And it was funny to see that or encouraging, I would say, to see that when we compare this with other biochemical estimates like the oxygen utilization rates, the study of Jenkins and Wallace near the Sargasso Sea, the values, the rates were very similar between the ETS and the oxygen utilization rates here. So they are more or less into this range of variability in the ocean. So it's not so far from other measurements here. Also, we compare ETS versus a tracer conservation model that was carried out by Gato Fernandez Castro at the stock station north of the Canary Islands, using climatological data of oxygen, disorganic carbon, and nitrate, comparing with different profiles after the spring bloom here in the Canaries of ETS activity. And the correlation was very good also. One interesting thing is that over 50% of the respiration took place in the mesopelagic zone, so between 200 and 1,000 meters, and the rest in the surface ocean. So there is a considerable respiration in the mesopelagic zone that needs to be taken into account. We have to say that this area is heavily influenced by carbon that is exported from the continental margin to the open ocean. And if we compare, in fact, with the Bermuda Atlantic time series, the BAT station, you can see that the POC mostly in the BATs are coming from sinking particles, and also there is another pool of this organic carbon coming from mixing after it's breaking the stratification during the springtime, while at the stock, most of the carbon is coming from lateral advection because there is little seasonal breaking of the thermocline, so the sinking is very also much lower. But at the end, most of the carbon that is responsive to organic carbon, in one case is coming from the surface, in the other it came from the lateral. And this is something which is interesting, and we can address in studies with ETS, where you can have this high resolution, temporal and spatial resolution in the water column. Also, there are other studies where we have found the strong correlation between suspended organic carbon and respiratory ETS activity. There was a cruise carried out following the central ridge in the Central Atlantic, and we found here very good correlation also between ETS and POC, or low sinking POC, in the intermediate waters of the Antarctic intermediate water, but also in the North Atlantic deep waters here, while there was almost no correlation with the dissolved organic carbon, which is something we would expect to have because it's very refractory in these regions. Also near the Canary Current and the Cape Verde frontal zone, an area which is also heavily exposed to transport of organic carbon from the coast to the open ocean. Here, the mesopelagic or POC explain about 65 to 70% of the variance of variability in the mesopelagic respiration here, and which is something that one would expect to find also, because there, as we said before, there is a high loading of organic carbon from the coast to the open ocean, of low sinking particles that they take some time. And there are several papers on this region and models, field work that they show that transport of carbon, of low sinking carbon from the coast to the open ocean, thousands of kilometers away, they are really important and can contribute to the respiration in this area. And finally, this is this cruise I showed you before. This is a Mediterranean cruise, and I want to point here a couple of things. Well, one is that again we have a significant good correlation between particular organic carbon and nitrogen with electron transport system. But what I want to show here is that the ETS activity allows to have a very high resolution in the vertical and also regional, and show variability of respiration in the water column with a precision that is not so easy to find with other ecological approaches or even biochemical approaches. So for instance, we can see in the Ionic Sea how the speed of water from the Adriatic Sea is bringing more carbon, and respiration is increasing relatively down to more than 2,000 meters there. And there is also some gradients of ETS activity in the surface ocean from the more oleotrophic region in the Eastern Mediterranean to the more enriched region in the Western Mediterranean. So there is a lot of information that we can infer from here, like the remineralization depth, or how different processes in the water column may affect respiration here. So this is one of the advantages of using a method like this one. And just to summarize, we can see that this enzymatic ETS technique represents a fast and sensitive method to address respiratory activity, which is not actual respiration, at a spatial down to some mesoscale and temporal scales, which are difficult to address with other ecological approaches. At a global regional scales, ETS-derived respiration, by using a low respiration ETS ratio, seems to agree with other biochemical estimates inferring oxygen consumption in the dark ocean. But we know that the R-ETS ratio may vary in cultures of marine bacteria and in the field up to an order of magnitude. So we need to constrain this variability. We need to have to run more experiments and field work to understand the scales and causes of this variability in the dark ocean. And finally, we need to explore the dependency of ETS-derived respiration on environmental variables in the dark ocean, like temperature, oxygen, and organic matter, quality of organic matter, to derive global parameterization that could be implemented in biochemical models. And this is one of the main goals that we have in this new Horizon 2020 project named Ocean ICU, Improving Carbon Understanding. Thank you very much. Happy
Great.
to take.
Thank you very much, Javier. That was an excellent first talk of our webinar today. And there's a couple of questions already coming in. And please also you all use the Q&A box. And I start. Question by Mauricio Urbina. Great talk, Javier. Thanks. Thinking about temporal scale, R changes pretty quickly depending on food, temperature, oxygen, and so on. But the question is, how close in time would ETS show such changes?
Yeah, that's a good question. It's a very, very good question. How is, it seems that it's not, let's say, months or something like that, could be days. Is the way that the enzymes adapt to the organism there, probably is days. So I think that the ETS in some way averages the respiratory activity during several days. And it depends also, I think this depends also on the organic matter and the activity of the organism, on how the enzymes adapt to that. But it's not an easy question to respond. Probably there's variability that between groups and between different situations.
Thank you. And another question. Is there a way to differentiate between suspended organic matter and sinking or locally exported organic matter?
Yeah, that's also a very good question. What we consider suspended or low sinking or wherever, these correlations had been made with Niskin bottle carbon. So all large, fast, uneven, large particles are not probably considered there. And so we assume that there are like low sinking particles, but it's true. I mean, what is suspended, what not? This is not suspended sinking or just fast sinking, because there is a gradient in the sinking velocity of the particles in the ocean. So one of the things it can be done now is to try to use a kind of large bottle like the no catchers and try to differentiate like this fraction that we call sinking and non-sinking. But even in the non-sinking or slow sinking particles, there is a gradient there. So I think we don't have a perfect method to say what is sinking or what is suspended, because it's a question of time. I think low sinking particles, sediment, or suspended particles, sediment is lower than the fast sinking particle. And many of them are not collected easily with semen troughs, for instance. And that's that's another problem. But so this, if I have to be honest, what we are correlating here is what you are collecting with the Niskin bottles, both for the ETS and for the POC and P1.
Yes, yeah, thank you. The follow-on question there, you mentioned that there's suspended material might be coming from the coasts, but you observe it thousands of kilometers away from the coast, and it there's some correlation with respiration. But if material is moved or transported over such long distances, then respiration rates probably must be very small. Why, or do you see a change in quality or a speed up of respiration when particles age or organic matter ages?
Yeah. There is a change in the quality in the CN ratio and so on. We are compiling a very, very large data sets on what we call here these slow sinking particles, and you can see changes from the coast to the open ocean. Not all the carbon is coming laterally. Of course, there is some coming from the surface, but the influx of carbon laterally is really important. It has been published in models and in fieldwork and box models and so on. And in these areas, you may find, and you can see gradients. In fact, you can see gradient when you do a cross section from the coast to the open ocean. You can see the gradients of particular organic carbon from the coast to the open ocean. There are a number of papers about that. Yes, at least in the area where we are working in the Northwest Africa, the Canary Current, and the Cape Verde region.
Yeah. Okay. Thank you. Then one question about the ratio, the respiration to ETS or ETS ratio. What value did you finally choose in your analysis? And okay, is it regionally varying or temporally varying? How do you decide?
I think until now,
is larger than one as well.
Yeah, until now we have been doing like baseline value to compare, which is this 0.1. That is something that we have found in the deep ocean, for instance, Mediterranean Sea, and in other regions. But obviously, you have an area in the mesopelagic where you have a lot of bacterial activity, as we had in the Canary Islands in this study, where we also measure other different proxies of bacteria, and they were extremely active. You must expect to have higher RETS. But we need to do a lot of still a lot of work on trying to constrain in this variability in the RETS ratio, which probably will vary regionally and will vary with the quality of the organic matter, and probably will vary also with temperature. Yeah, so what we are using, that is this 0.1, is a baseline, I would say.
Yes, right, fantastic, thank you. One very brief question, what portion of respiration do you expect comes from higher trophic levels from animals that you don't collect in your bottles or snow catchers that are too large or swim away? Okay, you mean from metazoans in the white column? I'm sure, I think that depends also. I mean, in some areas, you have very large and very thick scattering layers, for instance, where you have a lot of migrant fishes and also crustaceans. I think in those regions they must be important. But in general, at the global scale, I think they contribute little compared to the microbial respiration in general terms. But 1%? I think not sure how to tell you that. There is for the audience to answer. Yeah. I'm not going to put my hand on the fire for that. No. I think there are different papers published in this respect, and I think it depends also. It depends on the regions. I think in regions where you have a lot of migrants, maybe high latitude regions. Even those that they are migrating seasonally, they may contribute largely to this. But I really don't know. I'm sorry. Yes, no, that's fine. But it's hopefully stimulating to some people in the audience to answer such questions. Of course, it's science and interesting. Moving on. Okay, thank you, Javier. Excellent talk, and thank you all for the questions. Thanks very much. It's a pleasure. To our second speaker, Haichao Gu. He's currently a PhD student at GEOMAR in Kiel in our group. He's did his bachelor in the Ocean University in China with the exchange program with Tasmania, and then a master's at GEOMAR in Kiel, and he's now in the biochemical modeling group. And Haichao, the floor is yours to address the question of estimating respiration from the opposite viewpoint. And I look forward to your perspective.
Okay. Thanks, Andreas, for introducing me. And hi, everyone. I'm Haichao, and I'm from GEOMAR. Today, I'm very happy to share some of my recent research in this webinar. The topic is, can oxygen utilization rates track the long-term trend of mesopelagic respirations? And this topic is explored by my colleagues in GEOMAR, Arístegui, Andreas, Oschlies, and Wolfgang Kov, and myself. The preprint is online now. If you're interested in some technical details, the code, you can scan the QR code here later to the preprint. So first, I want to introduce some motivations of this research. So perhaps all the audience already know that the dissolved oxygen concentration in the ocean is declining. And these processes, the ocean deoxygenation, is widely regarded as a new stressor for the ecosystems. And the models, according to the model simulations, this deoxygenation process will continue. And by the end of this century, the ocean oxygen inventory is projected to decrease by about 3 to 4%. However, there's some mismatch between the model simulations and the observations. So for example, from 1960s to 2010s, observations show that there are about 2% of the total oxygen in the ocean has been lost, but that value in the model simulations is only 0.6. So we have very big mismatch between model simulations and observations. And this mismatch might indicate there's some deoxygenation mechanisms are not well represented in the models. These mechanisms include decreasing solubility and decreasing ventilations, and also possible changes in the consumption rates. And get some knowledge about how the oxygen consumption rates responds to the climate change will help us to understand quantitatively the mechanisms of the ocean deoxygenation, and also help the modelers to simulate the deoxygenation process better. And here I introduce one method. This is one biochemical method. It's called Oxygen Utilization Rates. It might have some potential ability to reconstruct the temperature changes of the respirations in the past. So in this green box, I show how the OUR is calculated. So first we calculate the apparent oxygen utilization, which is just the difference between saturated oxygen and the observed oxygen. So AUU gives some information about how many oxygen is consumed from the surface ocean to the sampled region. And OUR is just the ratio of the AUU gradient and the age gradient. So the age of the water is usually derived from some radioactive traces or the transient traces like CFCs in the real ocean. And the age of the water is defined as how long the water leaves the surface. So to better explain the concept of OUR, I show a schematic plot here. So you can see first we have the year's gas exchange near the surface. So near the surface, we always have high oxygen concentration waters. And then these waters, through the advections, move slowly to the ocean interior, like a box. The box move along the flows. So when the box moves, the respiration always happens in these boxes. So oxygen is consumed, AUU increases, and also the age increases. If we plot the age and AUU, it looks like this. So the age increases and AUU increases. And the slope of the AUU versus age gives some information about the respiration rates in the research regions. So, however, advection is not the only transport processes in the real ocean, and the model ocean as well. we have diffusions, which means during the box movements, it might have some exchange about oxygen and H traces with surrounding waters. So the respiration information might not be isolated into these boxes, but lost to the surrounding waters. And it might modify the H and AOU relationship here. To be more complicated, we also have the lateral mixing, which means some water came from different source regions, might go into these research sections and also modify the H and AOU relationship here. So I think it might be good. So I think it's necessary to give the question mark here for the H and H versus AOU slope, give the accurate respiration estimations. And at the beginning, I already clarify our motivations, which is we want to know whether OUR is a good proxy to measure to reconstruct the temperature changes of respirations as well. So we explore above questions in an ERSIS model foci. I won't introduce much details of this ERSIS model. I refer readers, if you are interested in this model, you can read the papers from Matters and Chen. But to be brief, this is an ERSIS model including a lot of components like atmosphere, ocean circulations, land, and of course, biochemical processes. In the ocean component, we have half-degree resolution, 46 layers. That is quite high for an ERSIS model. And to calculate OURs, we have the ideal H tracer. So idealized H tracer functions like a clock. So when the clock stays in the ocean surface, it will close. But when it leaves the surface, so the clock will open sorry, in the surface, the clock is closed. And then when it leaves the surface ocean, the clock open and measure the time, how long it leaves the surface. So this is some schematic plot for the biochemical processes that's simulated in this ERSIS model. So you see we have some nutrients, we have phytoplankton, zooplankton, and many processes. Again, I will not introduce much details here, but I will introduce how we simulate oxygen consumption rates. So here our true is basically local oxygen consumption rates. So it's basically just from the degradations of detritus and degradations of the dissolved organic matter. And also we don't include the temperature impacts on the decay rate as well. So it's kind of a simple model, but it's still useful. And the another thing I want to clarify here is we do all the calculations in the model ocean. We don't refer to any real ocean properties. So OUR is calculated as a proxy of oxygen consumption rates in the model ocean, and local or true respiration rates or oxygen is defined as the oxygen consumption rates from the degradation of detritus and dissolved organic matter in the model ocean as well. So the true respiration act like a ground truth for the OUR. So I have perfect reference to evaluate the OUR method. And here I introduce how we select study regions and show the distributions of the ADH, AOU, outcrops, and also research regions on several density surfaces. There are this dark blue bar shows where the research sections are. We select these sections following the criteria list here. So the echelons of the H and AOU should be parallel. The sections approximately follow the flow as well. And the third criteria is sections are perpendicular to the echelons of the H and AOU. So this criteria has been used by many field studies. And the purpose is to minimize the possible source water taps mixing, which might modify the H and AOU relationship. So just a name, the one is in North Atlantic is North Atlantic section, the one in the South is South Atlantic sections. Then here's this method. We have basically two simulations. One is a system model PI control simulations or pre-industrial control simulations. So in this simulation, we do not consider any anthropogenic effects. We don't have the carbon dioxide emissions from human activities. In another simulation, we have the transient simulations, in which we have the carbon dioxide emissions from human activities, and also we use the high carbon dioxide emission scenario for the future. And because we have to calculate OUR in the isopiconals, but the NEMO, the ocean component we use is in that coordinate. So I have to try remap all the variables from that coordinates to the sigma coordinates. And then we calculate the OURs using least regression line, and we calculate the mean true respiration rates, that depths at each density surfaces in the study sections. Afterwards, we calculate the OUR and true respiration integral from 200 meters to 1000 meters, which is defined as a mesopelagic zone. The final step is to do the statistic analysis of OUR and true respiration integral. So there are some results in the North Atlantic section. So the red color is true respiration integral, and the blue color is OUR integral. And the thick line is transient simulations, and the dashed line is pre-industrial control simulations. So the two features you can see from this figure. So 200 meters of the mesopelagic integrated OUR is approximately half of the integrated true respiration rates. And also both integrated true respiration and integrated OUR decrease with climate change. You can see the trend is quite clear. And in this figure, we show the vertical distributions of OUR and true respirations. So the shading color here is just the standard deviations. We also provide the standard deviations for OUR, but it's too small to be visible. From this figure, we can see that OUR is systematically smaller than true respiration rates, especially in the upper ocean. So what is the reasons for this difference between OUR and true respiration rates? So we know that near the surface, we have lots of food. So organisms are happy and consume a lot of oxygen. However, in the surface ocean, we have efficient air gas exchange. So in the surface or near the surface, oxygen is always high. So this high oxygen concentration does not allow the low oxygen below it. So it does not allow the AOU to be well preserved. So oxygen flux from atmosphere to the ocean does lead to very poor preserved imprints of respiration AOU. And OUR is calculated from AOU. So that might be the reason for the underestimate of the true respiration in OUR. This is not only in these models, but there's some other independent model studies, for example, by Kove and Keller 6 years ago, and they found the same phenomena. So let's see about climate change signal, and it's quite impressive. We can see that so we use the transient minus ESMP control simulations. So to isolate the climate change signal, that is a standard procedure in the model in the model study. So we can see that the true respiration and OUR both decrease in a very similar magnitude, with very similar magnitude. And here the plus and minus number just show the 95% confidence intervals. And we can see that at 95% confidence intervals, the integrated OUR is able to track the trends of integrated true respiration rates in the North Atlantic section. However, OUR performs differently in the South Atlantic section. So here, you can see two clear messages. The integrated true respiration is similar with integrated OUR. So you see the red line and blue line have kind of similar values. But the integrated true respiration decrease, the red line decrease, and the integrated OUR increases with climate change. So I have the divergent trend in this section. So the vertical distribution for OUR and true respiration also differ. The true respiration, it decrease almost like a Pavlov of the depth, but OUR shows a very complicated vertical patterns. So at the beginning, it decreased and then increased from 300 meters to around 400 meters and decrease again. This complicated vertical patterns might come from the mixing between different source water types. And again, the climate change signal. So again, the OUR shows divergent trend with true respirations, and also the correlation coefficient between true respiration and OUR is pretty low. It's minus 0.19. So which means the OUR, the OUR responds differently with response to climate change differently compared with the true respiration response to the climate change. So what are the reasons between the poor performance of the OUR here? So we provide several possible reasons. So assume that we do the OUR calculations in this red box, that is the study region. So with climate change, we have the ocean circulation changes in the warming ocean. And this ocean circulation changes might impact the composition of different water masses in this study region. And that will modify the H and AUU relationship. So the other reason might be that, not only in the research sections we have the respiration responses to the climate change, but in other regions, the respiration might also changes. For example, here is the South Atlantic section. It decreased. This is the true respiration, the mesopelagic respiration responses to the climate change. The purple color means decreasing respiration, and the orange color means respiration increase. The mesopelagic respiration increases. So you see that in the South Atlantic, the mesopelagic respiration decreases. However, we have a very significant respiration increases at around 40 Celsius degrees. And this increasing respiration signal might came to these regions and lead to the increasing OUR here. So the remote biochemical responses to climate change might be mapped into the study regions through mixing. And the mixing induced AUU and H from outside of the research section might induce an offsetting OUR trend with local true respirations, that like what we see in the South Atlantic section. So conclusions. First, OUR has potential ability to reconstruct the respiration rates integral in parts of the mesopelagic ocean. For example, in the North Atlantic section, where we have lots of measurements there. But in other parts of the mesopelagic ocean, the temperature trends diagnosed from OUR can be a very unreliable indicator of the trends in true respirations, like what we see in the South Atlantic section. So OUR, that is because OUR contains not only the respiration, the local respiration information, but also the mixing can induce some other signals. So OUR equals the local respiration rate plus mixing effects. And quantitative, so if we want to derive the aerobic respiration from OUR, we need accurate knowledge about mixing induced H and AUU in the study regions. However, in a transient ocean, it is still unresolved problems, so at least to my knowledge. And yeah, thanks for attention. And if you're interested, please feel free to contact me or go to my preprint. I'm open for any questions now.
Great. Thank you very much, Haichao. Very, very fascinating view on respiration estimates from the opposite end, the large-scale view, biochemical view. Now we have these two comprehensive presentations, direct Javier and direct and in situ measurements, and here the indirect biochemical tracer-based one. The first question is, how can you know in advance which area is where does your method can work well, and where would it not work well if you are out on the sea and don't have a good model?
Yeah, it's a good question. So basically, we need to go back to this plot. So if we have only one end members, if we don't have lots of source water mixing, so the section only came from one source region, so that might work. And also, if nearby we don't have some regions where we have a very strong feedbacks towards the climate change. For example, here, local decrease, and very nearby we have very strong increase in signal. These regions might not work, but for example, in the North Atlantic, we have relatively simple core waters, and also they only came from the mid-latitude regions where the respiration decreases. So that might work. So I think in the real ocean, if there's some water came from one region and along the pathways, the respiration rate feedbacks towards climate change is also the same, either decrease or either increase, that regions might work, but I don't know whether, yeah.
And how could you detect whether you have a one or two end member or mixing signals?
Yeah, because yeah, that is a good question. That is in the transit oceans, to my knowledge. I don't have any methods. Well, I don't know whether there's some papers address this issue. In the steady state ocean, we have several methods. For example, optimal multiparameter analysis. They're trying to separate the mixing effects and the biochemical effects. In the steady state ocean, it works, but in the transit ocean, especially the high carbon dioxide scenario ocean, I don't know. As I said, it's still an unresolved question to my knowledge.
Okay, thank you. And then here's a question by Christophe Rabouille. What changes for respiration do you expect with global change? Is it warming, slower circulation, changes in plankton production, changes in export? And what do you expect would be dominant?
So it depends on which regions you are studying. For example, in the high latitude, we have higher mixing, and the primary production might increase here in the high latitude regions. But in the temperate regions, in the middle latitude, because we have stronger stratifications, so we have less nutrients came from the deeper part, the primary production will decrease, and perhaps the respiration also decrease here. So depending on the regions where you study. On a global scale, I read several papers, for example, CMAP6 models. The export production have very large uncertainties here. So some models give positive, I mean globally. So there's some model give positive export production, some model give negative primary export production. So we still need to improve our understanding in that way.
Okay, thank you. And do you think that global estimates can still be useful, or can be useful based on the OUR methods?
Yes, it's a good question. That is what I'm researching. Use by all means and calculate OUR for the global ocean, and then try to get some trend now. But first, so if you select a larger area, OUR itself have a lot of source water, different source water types mixing, so OUR performs not good. So I still haven't got the result for the global OUR research, but so far, at least in the North Atlantic, it does not work. No, in the South Atlantic, I do some calculations in the South Atlantic. It have also in the Biomes province, it also have diverging trend. So that is what I can see here.
Okay, thank you. And if you have one wish free, would you rather have better oxygen measurements or better age measurements?
I want to both, but
one. What is more important?
Yeah, but I think the age is. I think the age is kind of more important because that only impacts not only impacts the oxygen concentration, but also impacts the anthropogenic carbon storage and the heat uptake, and a lot of questions are linked to the age measurements. So I would prefer the age measurements, but well, it's still good to have the high quality oxygen measurements as well.
Yes. And what do you think is the best tracers to measure or estimate age?
Well, currently people use CFC12 for the past few decades, and now they try to use SF6 because SF6 still increase and CFC12 start decrease now. I would like to see SF6 as a age tracer, but
okay.
that is to my knowledge.
Yes, but yeah, thank you very much, Haichao. That's some motivation for everybody in the audience to consider age tracers, which we also, I think, need for many other purposes to understand ventilation changes and any changes in the ocean. Great. Okay, that brings us to an end here. Thank you very much, Haichao, for your presentation, and thank you, Javier. We have a wide spectrum of methods to address this big scientific issue of mesopelagic respiration, which we got some global estimate, 1.2 petamole carbon per year that Javier arrived here, and so it's a huge portion of the fate of organic matter produced in the surface ocean, and we need to understand it if we want to understand the impact of climate change, of environmental change on the ocean and what fuels marine ecosystems. Thank you all very much. Thanks the audience for asking questions, for being here, for expanding the knowledge on ocean oxygen and possible changes. And I hope you have a few ideas how to proceed and how to improve our understanding. And we will be happy to have you here as a future speaker. We always try to merge two talks, one earlier career scientist and one more mid-career scientist, and ideally from different labs, different angles, to make this an interesting, exciting webinar for everybody. Please send us your feedback, and if you're interested to present your work, you're very welcome. Let us know to move to make the issue of raise the awareness for ocean deoxygenation and better understanding, and hopefully finding solutions to save the state of the ocean. Thank you very much. Have a good rest of the day, and see you soon at our next webinar. Goodbye.